And let's go to the whiteboard. All right. So this is the data encryption standard. And as you will see, it's, they're using everything we've done is like very elegant, right? The XOR and everything, very interesting. But now it almost starts to get like they're just like adding randomness or adding or jumbling or, things around, right? And so we're going to discuss how the data encryption standard works. We're going to do another one of those exercises that I do for participation, so kind of pay attention. And I'll give you a problem for you to think about, and you can get something similar to that on the exam, right? So pay close attention to it. But it should be fun. So these are, this is like puzzles, so it should be fun. All right, so let's go over desk here. Okay. Ooh. Yeah, so remember, this actually, we're almost concluding block ciphers at this point. This is, as you can see, it's usually the first third of the class is symmetric encryption and block ciphers. We will have a little bit of it next Thursday, but the week after, we're pretty much starting a new topic, which is asymmetric encryption. And that should be the second third of the course, which is RSA. So we'll get into that. That's different. RSA is different. It's more like algebra than, say, like what we've been doing here. All right, so let's kind of look at block ciphers. We're going to provide the formal definition of block ciphers. Okay, and in particular, as I said, we are focusing on DES. I don't cover AES in this class because it requires like matrix algebra, right? So if you've taken like 265, you know what I'm talking about, like the NumPy operations there. And so it's just more advanced. I mean, it requires a little bit more work. So, you can implement it for your term project if you choose to. All right, so as you know, DES stands for the Data Encryption Standard. So we'll just talk a little briefly of some of the history. So Data Encryption Standard. Okay, so this is block cipher. So remember, the main idea is that you have n bits, right? So n bits of a block, and then it's going to go through, you have two encryption and decryption algorithms based on XOR, but there's more to them than just XOR. And then that produces n bits, right? So that's kind of the formal definition of this, okay? Just like that. And then, of course, we have one key. So that has been the constant in everything that we've done so far, is that we always just have one key of k bits. Okay, so a little bit of history. So this algorithm started in around the 1970s. So think about that, right? So if you think about the context of history, right? Before the 40s, it was like substitution ciphers, the Enigma in the 40s, which is what was, I don't know if you guys saw the talk of the NSA person that came last week. So he brought an Enigma to the campus and gave a talk. So hopefully some of you went to that. And so, so that was a type of a substitution thing as well. That was in the 40s. Claude Shannon started, with the OTP in the 40s, 50s. And then around the 1970s, that's where we actually get like a modern type of an encryption. And this was done by IBM. All right, so IBM computers in the 1970s. Around 1997, so around 1997, DES was broken by an exhaustive search, okay? So DES was broken in 1997, and then around 2000, or in 2000, around that time, AES was adopted, and this is still today, so 25 years later, for symmetric encryption, the methodology. Now, you may find that there's like something called blowfish or something, funny names for different things, but inside it's AES, you know what I mean? So they may have a few specifications. If somebody implements it at some organization, they give it a specific name, but it's still AES, the Advanced Encryption Standard. And there's, the NSA, who is in charge of that cryptography stuff, they're constantly trying to break it with that actually not really to spy, but really to protect, make sure that it's still reliable, basically, right? And so that's really the idea. So there is legislation right now. So I guess I should say the last piece of history is that there is legislation right now because there's a concern that in 15 years, there could be quantum computers. Who knows? They may be in 15 years or in 115 years. Nobody knows. But if it happens in 15 years, those computers could possibly break these algorithms. So there's a danger there or a concern. And so there's people doing research on making these algorithms what is called quantum compliant. Right. So there's that initiative, but there's no solution. It's just like research and a goal. Anyway, that's kind of the history of it all. Okay. And so so DES is considered one of the most studied techniques in cryptography, actually. And so we're just going to take a peek as to how it works. Okay. And like I said, I'm not asking you guys to implement it, but because it is pretty involved. All right, so let's go ahead and get started. Any questions before I? All right, so DES has a few ideas. Okay, so there's a few ideas. At the end of the day, you are XORing bits, but there's more to it, right? Like there's steps in the process. Okay, but the basic idea, like at the center of it, is that you have something called a Feistel network. Okay, that's like the basic idea. Okay, so I'll write this down. And I think actually on GitHub, I already have these notes uploaded, so you can take a look at those. You can print them out if you'd like. All right, so the basic idea, or not GitHub, sorry, Brightspace. So the basic idea is to build a Feistel network. To build and this is the name. Feistel is probably the person that came up with the idea here. So Feistel network, okay? And as you will see, the Feistel network is just, you take a block, you split it, and then you like move it around in a specific scheme, and then you end up with another block. It's usually how it is, right? You have an input block and an output block, but inside you do something. And in this case, you implement a Feistel network. Okay. So this involves also a set of functions. Okay. So there's going to be some functions in here. And so we'll talk about the functions in a little bit, but there's also DES uses some functions. Let's just say functions, and again to map n bits to n bits. N bits to n bits. Okay. So that's, very, very common thing, okay, that we are usually, as I said, an input of a block, do something to that block, and then produce another block of the same size. So we build a Feistel network, but the Feistel network also has these functions in it. And what these functions do is they take a block of n bits and produce another block of n bits, okay, in the process. All right, so now let's define the scheme, okay? Now we can formally define, before I do that, before I talk about the Feistel network, I'm just going to more formally define these functions. So let's just say we define the functions as f1, comma, f2, dot, 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 all the way to fd as basically, and we've done this before, a function that takes a sequence of bits of size n and produces a sequence of bits of size n. All right, so that's basically the thing. So in the past, we've done things where we had a much smaller seed and produced something much larger. In this case, the sequence of zeros and ones is still of the same size. All right, so now pay attention to this part, because this is the part that's going to be basically the practice quiz. All right, and so let's try to understand it. Okay, so the network. All right, so that's let's think about the Feistel network. And I'm going to change color to red. Okay. Okay, so the Feistel network. Okay. So the Feistel network is basically, it takes a block and produces a block of the same size, but it's going to rearrange the blocks in a specific way, right? So we're going to start with a block over here of a specific size. And we're going to take that block. Let's say it's going to be 2 times n bits. So 2 times n, okay? And we're going to split it in half. Okay, so we break the block in half. So now each block is n bits, because this was 2n, right? So this is n bits, n bits, and n bits. So they're the same size, which is what's important. We're also going to give them names here. Okay, this will be important. And there's an index associated with each block, okay? So that we can implement this in code, for instance. So we're going to say, oops, that this one is right and this one is left, okay? And the index here will be 0 and 0. So then this block needs to be changed, right? So that's what the Feistel network will want to do. We'll want to produce another block of the same size, still in half, okay? So this one we're going to call R1, and this one is going to be L1, all right, for the next index, but they're still right and left. Now, the key thing is how the jumbling, if you will, or, the scrambling of these blocks is going to happen. Okay, so the basic algorithm of the Feistel network is to do that. So that's basically simple enough, right? So right 0 becomes left 1 in the next iteration. Going forward, now remember, something that's important is we're going in that direction. Okay, obviously we need to come back in the other direction. So now this one's a little bit more tricky. To get R1, we are going to take R0, and R0 will go into one of those functions that we defined previously. Remember, and these functions also do a conversion. But in the end, you have a block of n bits, and it produces a block of n bits. You see that? That's the data encryption standard. Okay, so we go over here, and this is going to be called F1. And it's a function that takes block R0, right? It's going to modify it, and then that block comes out here. Then there's going to be an XOR operation, as you might imagine, with block L0. And then the result of this is what becomes R1. Got it? That's it. This is the Feistel network. And then you just repeat this for several iterations. And that's part of this. So as you can see, what's important here, it's not about memorizing it per se, but it's about like understanding that the data encryption standard just tries to scramble things a lot. Okay, it's kind of the idea. All right, then we have, which is, it's like an intuitive thing that humans might do. All right, so now let's look at the next one. We're going to do a few iterations of this. So let's do, remember the blocks are still n bits. That hasn't changed. So this is R2 and this is left 2. Okay, so the same idea would apply. Now R1 just kind of slides down and becomes L2. Okay, and then here we have another function F2, right? That's the function 2, which takes R1, slides into the function. Remember that just takes n bits and produces n bits in some scheme. And then what comes out of F2 gets XORed with L1, and then that will slide basically into R2. Okay, so that is the Feistel network, and that's part of the data encryption standard. Okay, then, I'm just gonna this would continue, let's say for 16 rounds or however many you define. Let's just kind of do the last one here. Okay, so we're gonna have this. And actually, let me give myself a little bit more room. All right, so the final one will be RD and LD, and this is going to be N bits and N bits, right, to produce a block that is 2N, and this is the output, basically. All right, and we're just going to do the final part, which is really the same as before. We can call this one RD minus 1, right? And this one would be left D minus 1. Just like that. And so the process should be the same. So this one just slides and becomes LD. And then for the last, for RD, we're going to have a function FD. Okay. So we can, that's a function. RD goes into that function. It gets changed, right? And now we have, we have an XOR operation here between that and this one, and that becomes RD. Does that make sense? So that is basically the Feistel network, which is part of the algorithm of the data encryption standard. Okay. So now, therefore, we can generalize this process into some relationships. So we can say that if we want Li, then that's just going to be equal to Ri minus 1, right? So that kind of generalizes to that. You can see that here, right? It's just basically this one. So this one is, because this just slides all the way over here, okay? Now, if we do the other one, that one's a little bit more tricky. So we can say Ri is what? It is Ri, right? So it's going to be L, right? So it's going to be L I minus 1, and then XOR, oops, sorry, that's not an XOR. XOR with what? We need to do Fi of Ri minus 1, right? And then that becomes like our generalization. Do you guys see that? Does this make sense, guys? Any questions? Clear? All right, great. So yeah, so again, this is just to kind of get a feel for how it works, right? If you wanted to implement this in code, etc., and just to see the pattern. So this is just part of DES. It's not the whole thing. We still need to define a little bit of the F functions, for instance, right? So, but we can think of it basically if you want, right? Now DES is like 3 things. The XOR, obviously, that we knew was happening. This Feistel network that's happening here, but also remember that there's these F functions that take a vector and produce another, a block and produce another block of the same size. So we may still need to define those F functions, which we'll do that in a sec, but otherwise those 3 things are the basic idea of DES, like if you wanted to speak more of it. Any questions? Yeah, please go ahead.
So to get the next L in the sequence, it's just the last R copied, and then the one that actually changes is the R1 in the next sequence, right? That's the one that gets XORed with the function.
Right. So this one, to become this, right? it like slides down. Imagine there's a slide, nothing,
Okay.
no change whatsoever.
Gotcha.
Yeah. And then for this one, we need a result of an XOR operation between this one. So you can imagine this one would have slide, but it doesn't. It starts out, and then you need to take this one and run it through a function that makes that block into another block.
Right.
And that gets XORed with this one and to produce the final one.
Oh.
That's how it works. Why? I mean, ask Feistel. All right, but that was the data encryption standard. Got it? Does it make sense, guys? Yeah? All right, so now let's do the exercise. And again, it's just, kind of fun to think about this a little bit more deeply. All right, so what you're going to do now is you're going to do it in reverse. Right, so if we went that way, now do it in reverse. Right, and just, let's think through this exercise. So let me write it out for you. So take out a sheet of paper. And so let's do this, let's call it the inverse, basically. So the inverse, right? So given the previous logic, how would you invert the process? That's the question, right? How do you go in the Feistel network? But in the opposite direction, right? Reverse it. So I'm going to give you, for instance, a diagram, right? So let's say I'm going to do it in the next page. So I'm going to give you this, right? I'm going to give you that. Okay, so this is going to be R I plus 1, and this is left I plus 1, and this is going to be Li, and this is going to be Ri. And the Feistel, I'll draw the network. It's still the same one. So, it doesn't change. And this is going to be, right, the function. Let me make that bigger, sorry. So that's going to be, I plus 1. I'm just giving you notation so that you can, we can all write it the same way. So this is XOR, correct? And then this is the Li, and then this just goes over here, right? But the key question is that now, before we were going in that direction, now you're going in this direction, right? The inverse of it. So then what the question we want to answer is, what is Ri? Do you see that? Given these. So you have to write this Ri equals this, right? But in the other direction. And what is Li? So think of the logic in reverse. So what you have to give me is just like before, we had these two, right? In the direction forward. Now I need these two, but in the direction in the inverse. Questions? Yeah. So try it out, okay, as an exercise, and see if it may not be as difficult as you think. Just think of the movement in one direction and how it would be equal. Okay. Take a few minutes. pause the video.